Hello and welcome to workshop number 5 in Widener's Mechanical Engineering 474 Introduction to Finite Element Analysis. For this week's workshop, we will be solving the problem shown here on the screen, in which we have embedded a 1 inch by 1 inch by 5 inch high bar made out of steel, and we're going to embed that into a 2 inch by 1 inch by 6 inch aluminum part. And then the idea is that we're going to grab this thing from both ends, we're going to apply a compressive deflection to it, and we're going to look to see how the stress builds up at the interface of those two parts. So those two bars are perfectly glued together. Looks like I left out here that first bar, the smaller bar, is made of steel, and the outer bar is made out of aluminum, and then we're just going to compress those two pieces together. So this is the problem that we intend to solve. For this particular workshop then, we're going to be using the Abaqus CAE Student Edition 2017. I'm sure if you're using a different version, for the most part, the buttons and the functions should be very similar. However, it's possible that there could be some differences depending upon which version you are using. So we'll start out here in our part module. The main new things that you're going to learn in this particular module, or in this particular workshop rather, is doing some different ways of partitioning parts in a 3D part especially. That's kind of the key new feature, and depending upon how it is that you decide to solve the problem, you could also do some things with interactions and with ties. However, I'm going to show you what I think is a faster way of doing that, in which we will model this as one part. We will definitely take advantage of symmetry faces as well, but by just modeling it as one part, we will automatically create those tie surfaces and faces, and we won't have to do that ourselves. So let's start out here in the part module. We will create a new part. As you may have seen in this particular example, we are doing this one in inches. So in the past we've been dealing primarily in metric, so now we're going to be working in inches, which means our modulus values are in PSI. The reason I bring that up now is that when we go to enter in the size, we could actually reduce this number pretty drastically if we'd like, so that way the grid that they're going to put up on the screen will fit our part much better. So I'm going to change this to an approximate size of 20. You'll see here comes our grid, and what we're going to start out modeling is going to be, well, first of all, we should bring up that we can do this with 3 different symmetry planes. So we could cut the problem in half coming up and down, we can cut it top to bottom, and then we can also slice it in the depth as well. So we're going to go ahead and cut that in 3 places, which means that if this larger piece is 2 inches wide by 1 inch deep by 6 inches high, we can model just this upper left, let's say front quadrant. So it's going to be 1 inch wide by 3 inches tall by a ½ inch deep. So that's what we're going to go ahead and start out modeling. So I'm going to use my rectangle tool. Abaqus asked me where do I want this rectangle to start, so I'm going to say from 0, 0. And since I like to draw the upper left, we're going to now come to -1, 3. Okay, so that's going to give us our 1 by 3 section. I'm all done drawing, and I'm all done with a sketch. And for a depth, we're going to extrude to a depth of a ½ inch. And that's going to get us our initial shape that we need. Now we do need to create the steel core. So what we're going to do for that then, the steel core, it says, is 1 by 1 by 5, and it's centered. So if we're only going to do the upper left here, it needs to be a ½ inch wide by 2½ inches tall, and then it's the full ½ inch deep. So if we come back here to our model, the way that I'm going to accomplish that is by first partitioning this front face, and then I'm going to extrude that through the thickness of the part. So I'm going to start off here. If I click and hold on this first button here for extruding, you'll see there's lots of different ways to partition a face. We've covered some of this discussion in previous classes. For this one, we're going to partition using a sketch, and you'll see that Abaqus comes up and asks you to select the faces for my partition. So I'm going to say I'm going to do that on this front face, and then I'll say done. And then the next thing that Abaqus asks me to do is to select an edge that will appear vertical and on the right. So as I go to sketch, I would like for this one to appear vertical and on the right. So all that does is it just orients my face here, so that way I know what I'm looking at when I go to draw my partition. So we can again use the rectangle tool. I'm going to show you a slightly different way to do that this time. I'm just going to do a point and click here first. So I'm going to go from down here and I'm going to drag it up roughly where I think it would need to be. And here's my rectangle. But now if I would like to fix some of those dimensions, I can come down here and click on the Add Dimension button. So for the width, if I click on that width first and I drag it up and click again, Abaqus asks me what's my new dimension. So we need this to be a 1/2 inch wide. And then for a height, I'll do the same thing. And this one I need to be 2.5 inches. So I've now created this core here that is a 1/2 inch by 2.5 inches. So I am all done drawing. And I'll see now I've got my partitioned face. So now I need to figure out how do I make that go through the depth of my object. So again, if I look at some of the other buttons in here, there's a partition cell button, which you'll see there's just like in the sketch button, or the face button rather, there's quite a few different options. The one that we're going to use today is the partition cell using extruding or sweeping edges. So you'll see now Abaqus comes up and asks me to select one or more edges in the same plane to sweep. So I'm going to say I want this one, and then holding down Shift, I'll click on the second edge, and I've selected that partition that I just drew. And when I say done, Abaqus now gives me a few options. I can either extrude it along a direction, which is what we're going to do here, or if you wanted to sweep it along a direction, you could also use that feature as well. So we're going to extrude, and I just want to click on the depth. You'll see the arrow shows up. So depending upon where your plane was that you had drawn, perhaps you need to extrude into the page or out of the page. Kind of just depends on which way you went. In this particular case, Abaqus has assumed the correct direction. I can see it's pointing into the page. So when I say OK and create partition, Abaqus has now created this partition where I've got two different cells here. Something I would like to do further, just to help me from a meshing standpoint, what we're going to find is that if I go to try to mesh this aluminum portion, the outer portion, as it goes to wrap around the corner, this could cause some difficulty. So perhaps to make things easier, I'm going to just continue this partition straight across, and that way it will allow me to make that partition or the meshing there a little bit easier. I just need to remember when I assign properties that it's only this core region here that's going to be different. So we're going to use the same method here. I'm going to partition using a sketch. It asks me to select the faces, so I'm going to click out here on this outer section. And again, it's going to ask me for a face vertical and on the right. So I will just choose this face again. So now I've got a little portion here. And you'll see that conveniently it can allow me to snap to that corner, which is exactly what I want. I just want to drag this line straight across so that I partition along that same height. That's all I needed to do, so I'm going to say I'm done, and I'm done sketching that geometry. However, I have only partitioned the face at this point, so I need to follow that same step that I did before of partitioning the cell. Abaqus is going to ask me now, since I've got more than one cell on the screen, to select which one I want to partition, so I'm going to do that outer block and say done. And then I'm just going to choose that one new edge that I created. I'm going to extrude again, and I'm going to go with that same angle, the same edge rather, and it once again has assumed the correct direction, and I'll create that partition. So now I've got a block on the top, a block on the left, and a block on the right. Okay, so we have now partitioned this bar into 3 segments, and we are done with the part module. If I come down to property, I need to create 2 properties, one for aluminum, one for steel. The aluminum property is going to be 10 times 10 to the 6th psi. So we will create a material. We're going to call it aluminum. It has mechanical elastic properties. And again, it was 10 e to the 6th for the Young's modulus, and a Poisson's ratio, let's say it's 0.22. Okay, and I'm going to say OK. We also need to create one for steel, so let's go ahead and do that one right now. We'll call it steel. And very similar to the last one here, Young's modulus this time, however, was 30 times 10 to the 6th, so 30 e to the 6th. And we'll just do 0.23 for a Poisson's ratio. So I've now created those two materials, but just like previous lessons we've done, we also need to create a section. So we're going to call this one aluminum. It is solid, it's homogeneous, and I see that I've got a few materials to select from, so I'm going to link this up to my aluminum material, and that creates the first section. And for the second section, we will call this one steel. It's also homogeneous, and we'll choose steel from our drop-down, and we're good to go. So we have now created two materials and two sections. So now I need to assign those sections to my part. So Abaqus asked me first, select the regions to be assigned a section. So why don't we go ahead, we'll do the steel one first, which is the core. So I'm going to click on that section. And in my drop-downs, I will highlight steel. And I now see that that section, the core section, has changed colors. So I know that the section property has been assigned. I'm still in that assigned section area right now, so Abaqus is asking me if I want to select additional regions for a new section. So I'm going to go ahead and select the two remaining cells here and say done. And those are going to be aluminum. And when I say OK, I see that those two sections as well have changed colors, indicating that I have now assigned a section. So what's nice about doing it this way, using those partitions and just selecting different section properties, is that Abaqus assumes at the boundary of those sections is a perfect tie constraint. So it still sort of views it almost as if it is one part, and that those two sections will be perfectly tied together, and I don't need to go in and create additional tie constraints. If you created these as two separate parts, which you certainly could do as well, you would just need to go in under interactions and set up a tie constraint and tie those faces together so that that way those parts would act as one. So it just kind of creates an additional step. You'd have to set up contact, you'd have to set up all those things as well. So I just find this a little bit easier now that I can do it as one part, and at that boundary it has assumed a perfect connection. If you were trying to simulate something though where we were welding these together or gluing them together or somehow fastening them together, and that was the part of the modeling that you were interested in, this method may not be the best then, as it wouldn't really allow you to do much studies on that interface. So that being said, I do think for our problem this is the quickest way, so we'll move on to an assembly. We always need an assembly, even if it's only one part, such as the case here. So we will bring that one part into our assembly. And when we come into steps, unlike last time, we are now back to just a static general step. We'll call it load. And maybe just to make things interesting, we can try to force some additional steps, some additional increments here. So we'll just say I want to see 10 steps, or 10 increments rather, and I'm going to force the problem to kind of solve that way. Interactions, we don't have any interactions, it's all one part. If we come down to load, I do need to create all of my symmetry boundary conditions and then also apply my compressive displacement to this part as well. So currently we are on the load step, so why don't we just change this one to the initial step where we can set all of our initial conditions. Symmetry again is under boundary conditions, so I'll click on boundary conditions, and let's just go in order. So we'll do X symmetry first. It is under the symmetry type. So when I say continue, just remember that we need to choose the faces that are normal to that direction. So here's my X direction. So these faces here would be subject to X symmetry. So I'm going to click on both of these faces and say done. And I will choose the X symmetry boundary condition, and I now see that those faces are subjected to that boundary condition. If we will do the same for the Y direction, so let's go ahead and rotate a bit here, so that way we can see bottom of my face here. Whoop, getting a little crooked. So here's the bottom portion, so I can see Y is going here, so I just want to apply a symmetry boundary condition to this bottom face. So I will call it Y sim. It's still under the symmetry type. And I'm going to click on these two faces. And it is a Y symmetry boundary condition. Maybe just to help myself out, I'm going to use my tool up here to go back to the standard views. And now I need to get that back face so that I can apply my Z boundary condition as well. So once again, it's a boundary condition. We're going to call this one Z symmetry. And I need to get this entire back face of the, oops, got to hold down Shift, the whole entire back face here. So we'll get all three of those faces, and I'm going to apply a Z symmetry boundary condition. So I've now created all of the different boundary conditions that I needed. I would also like to apply my compressive forces here. So that's going to take place not in the initial step, but in the loading step. And that we can also do that with a boundary condition, however. So I will click on the boundary conditions. I will call it maybe deflect. Except now it is not a symmetry, it's a displacement. And I'm going to apply that on this top face. And what was the value that we were going to put in? Just a really tiny value, a thousandth of an inch. And this is going to be in the 2 direction. And as I can see, positive is up, so if I want to compress it, I need to go negative 0.0005. So we know that in order to get that type of deflection on a solid block like this, that does actually take a significant amount of load, so that's why we've chosen such a small value. We've also kind of constrained this problem a lot, so we may see some buckling, especially in the student edition, since we're limited in the number of nodes and elements that we can have. So when I say OK here, I can see all these arrows coming down, which is correct. That's the direction I was hoping. So I have completed my boundary conditions and initial conditions that I needed to apply for this particular problem. So we will move on now to the mesh. It's always a good idea. Oh, I'm going to remember this time to change it to part. It's always the part I forget. This time I remembered. So we're going to check the element types, and I will just select the entire problem. I just kind of wanted to show you that by default it has gone to 3D stress, which is good. That's what we wanted. There's lots of different options in here. We're not really going to get into these options in our particular class, but there are many options depending upon how complex your problem is. That some of these features may help you arrive at solutions. However, it's always important to understand what you have clicked on in here, just because of what some of those things may mean. So if I say OK, I'm happy with that. I need to seed the part. So let's just see what the default one looks like. That could work. That might be not too many nodes. Let's say OK, and then actually mesh it here and see how many elements that created. It only created 96 elements, so we may be all right. Maybe we can crank that up even a little bit further, just to get a few more elements on there. Obviously, we are somewhat limited in how many we can have, but we've got 3 through the thickness. You'll see that extra little partitioning that we did has really helped to keep everything all nice and square coming around that corner. So really that's kind of where you would see that impact. If we had not done that additional step to partition it a bit further, we could have ended up with some kind of funny looking elements around those corners. Which is important because if we're interested in the stress at that interface, we certainly don't want to artificially create something just because of the shape of our elements. So I'm pretty happy with this one. We'll find out if we're under the number that we need for the student edition. So I'll move on to the job here. We'll create a job that is now just called maybe work 5. I'll say continue. And we'll accept all the defaults here since we're not doing any parallelization or anything. So if I open up my job manager, I will submit the job. And let's see if I have exceeded the number of elements and nodes. It looks like maybe it has not. So if I come in here to monitor, and again, if you recall, I limited the size of the increments that we could take within that step. So I've kind of forced Abaqus to do some smaller increments, just so that maybe if we wanted to see how the stress built up slowly, we could do that. So there you see it completed pretty quickly. It did my 10 increments, so I should now be able to see those loads in a shorter time frame. So if I look at the results, here's my deformed shape, undeformed shape. That's pretty cool. So clearly it's magnified everything. We can see down here my scale factor is 6 times 10 to the second. So it's 600 times magnified. If you wanted to see it without that magnification on, we could just change this uniform to be 1 up here. And now you won't even notice anything when I click on the 2. So that's why Abaqus does that, because otherwise it could be just way too little an amount of deformation there that you may be staring at your screen trying to figure out if you actually did anything or not. So here we can see, though, we did successfully compress things. It looks pretty good. If I bring up my stress contour, you can see there's a very sharp difference between those two materials, because what's happened here is we've applied those forces to the softer aluminum, which has definitely squeezed and bulged out, and you can see the steel has not done nearly as much. But we could also look now maybe at just the magnitudes of deflections. So you can see there's a lot more happening up there in the aluminum portions, and then it's kind of stays a little bit more stable in the steel portion. If we also go back to our trick, the ODB display options, and we do our mirror and pattern, we should be able to do all 3 of these to create kind of what the full piece would have looked like. So you can see in here we've got our solid steel core surrounded by our aluminum, so it looks like we have done this correctly the way I was hoping we would. And so we can kind of see how the whole bar worked when we compressed it. Also, one of the other things we can do, if we look at, we can also animate this. So if I animate my problem, we can kind of watch how the stress builds up rather through an animation. We can slow that down or speed it up. If I continue to kind of slow it down, we can also have it just play once if we wanted to. So you can have it, kind of just animate that thing the whole way through, and then we can hit the play button again. It'll go back through it a second time. So there's lots of cool things that you can do there if you wanted to. You can create some different videos this way too if you needed to for a marketing presentation, etc. But anyway, so we have solved workshop number 5, which involved embedding a stiffer material inside of a softer material. So maybe the main new thing that we learned here was a method for solving this with just one part, and different ways of partitioning a 3D object, and then applying multiple symmetry faces again to a 3D solid. We've also done primarily 2D problems, so this was a good example here showing you how to use some of those same features except on a 3D problem. So if you have any thoughts or questions, please feel free to leave some comments or reach out to me in class. And also take a look at some of the other videos that we've posted to help you out with some of the other workshops. And once again, this is for ME474 for the Widener Introduction to Finite Element class. And stay tuned for workshop number 6, where I believe we will be taking a look at a dynamic problem for the first time. We're going to try to solve a very basic dynamic problem where we're going to kind of smash 2 cubes into each other of different sizes and different materials, and we will see how they behave. So tune in next time. Thanks a lot, and we'll see you in class.